Let's start. Our first speaker for today is Tobias Elkholm, and he's going to tell us about Skein prices and curve counting.
Okay, thanks. I want to thank the organizers for the invitation. It's a great pleasure to be here. And so I'm going to try to tell you some story about, in a sense, applications of something we have been doing for a couple of years by now, this Skein-valued holomorphic curve counting, and it gives a very enumerative, geometric, or string theoretic, if you want, view on what's known as Skein trace. So if you never heard about Skein traces, I'll tell you what it is, and it allows you to generalize some of the results there, and also to prove new things. And I'm going to try to illustrate that. But I will start by explaining what this Skein-valued curve counting is about, and this whole thing, if I compare to some of the other talks, it will be a little bit less algebraic than what you're used to, but hopefully still understandable. So this is something we developed with Vivek Shende over by now many years, and the setup is that of curve counting in dimension 3. So we have a symplectic Calabi-Yau threefold. It is most often actually not compact. If it's not compact, we have some control at infinity so that curves do not escape there. We will see in examples, it's pretty clear that there is no problem in that respect. And then we have a Maslov zero Lagrangian, and we'll consider both compact Lagrangians and these non-compact Lagrangians that we've seen in the conference that have some kind of cylindrical end. So they end on some Lagrangian at infinity if X has some boundary. And of course, we need some almost complex structure that's compatible with this omega. And then we do, as usual in Gromov-Witten or Floer theory or something, we look at holomorphic curves, so that those are solutions to the Cauchy-Riemann equation that you see there, and they take the boundary of the holomorphic curve into the Lagrangian and the rest into X. Okay, so this, and here's kind of explanation of why this dimension 3 and why Maslov 0. So this Cauchy-Riemann operator is Fredholm operator, so you can compute the expected dimension of the space of solutions, and this is a sort of a famous index formula, and it's the dimension of the ambient space, complex dimension of the ambient space, -3 times Euler characteristic of the surface, and then plus a Chern class contribution, so this kind of relative Chern class, and the first term in this case vanishes because dimension ambient space is dimension complex dimension 3, so real dimension 6. And the second term vanishes because we are in Calabi-Yau case, so first Chern class is 0, and somehow this Maslov is 0 means that also counterpart for relative homology classes also hold. So this means that if you take any holomorphic curve of any topology and map it in there, then you expect that if you wiggle things a little bit, it should be a zero-dimensional space. So everything is rigid, and therefore it's tempting to try to count the points in this space, and then somehow it's not always a manifold, it's rather an orbifold, but so points should have some rational weights, and you count them up, and you get the count. And if you do closed Gromov-Witten theory, if there is no L there, then this count is invariant under deformation. But when you do open curve counts, the corresponding count is not invariant under deformation, because in this space there are codimension 1 boundaries. So that's what Amanda also told us about. So I'll draw the boundaries in a little bit. So kind of long story short, the main idea about this Skein-valued curve counts is that if you look at this boundary, then you can somehow just mod out by these wall crossings, and then of course you would get a deformation invariant count if you somehow say that things on one side of the wall is equal to things on the other side. Maybe it's all 0, but you certainly get invariance. And as it turns out, and I'll show you in the next slide, the wall crossings are exactly equal to what's known as the Humphreys-Skein relation in knot theory. So we kind of come back to this, of course, not completely unexpected. It goes back to kind of work of Witten and Oguri-Vafa and so on. So somehow maybe not exactly these, but similar things. So we're not the first to see the connection between knot theory and holomorphic curves, but here it's kind of very manifest. So let me just remind you what the Skein module of a three-manifold is. So L here is a three-manifold. So we take some kind of coefficient ring which has two variables. It's always called A and Z. And then we take kind of a module generated by all isotopic classes of links, actually framed links in this manifold. So you should think of not just a knot, but a knot with some kind of normal vector field, so thin ribbon. And we take that, but then we quotient out by three relations. And these three relations are drawn here. And what is intended to be shown here is that what you see a little piece of the link inside the ball, and outside it does whatever it wants. So in the first equation, you see three links which are different only in this little ball. And we introduce the relation that the difference of the over and the under crossing is equal to this Z variable times the splicing. Okay. So this is the first Skein relation. The second Skein relation is here written in a little bit odd way, maybe if you're a knot theorist. So typically it's viewed as the normalization of what is the value of the unknot. So unknot here, this little circle is a circle inside the coordinate 3 ball, which lives in a plane. And we're saying that its value is C times that circle is equal to A minus A inverse. And the third relation is somehow telling you what happens when you change the framing. So what you should imagine here is that the picture is drawn again in a ball, and you take the blackboard framing. So somehow you can undo a twist by multiplying by A, or if the twist happens to be negative, you get A inverse. And so now you can ask, okay, so you associate this sort of crazy module to any three manifold, and you get something. The question is, what is it? Well, this Humphrey polynomial for knots in S3 is actually coming from the module for S3. So if L here is S3, then you can check that you can actually reduce any link to an empty link. So a bunch of unknots first, then you take away the unknots. So every link is actually equal in this module to some polynomial times the empty link. And that polynomial is known as Humphrey polynomial. And it's a kind of very rich knot invariant that does a lot of good for you. And if you have other three manifolds, somehow you have to calculate this Skein module in many ways. So we'll see it for the torus times R and solid torus times R. No, solid torus and solid torus times R. Then it's known, and I don't know, for RP3 it's some infinitely many generators. But anyway, it's a kind of nice story. It's not known for every manifold, but it's certainly related to something like free homotopy classes of loops and so on. Okay, this is the Skein. And now let me try to explain to you why this Skein business appears for holomorphic curves, and then how it cures this wall crossing business. So if you look at these curves with boundary in L, then, as I said, for generic complex structure, generic perturbation data, you have to say, the curves are just sitting there, and of course, generically, they will be embedded. So, crossing codimension 1, so they're embedded on the boundary in particular, and the interior of the curve, so curve is two-dimensional, so interior of curve will generically be disjoint from the Lagrangian itself, right? So it's 2 plus 3 is 5, and we're in 6, so that should be generically the case. And so we have to see what happens when we have some deformation parameter. Let's say imagine you deform complex structure, for example. So in this first picture, I'm drawing some moduli space of curves of Euler characteristic chi0. and as so you should think about the equation something like xy is equal to epsilon or something like this, right? And you take epsilon to 0. So you see these two, the two parts of the boundary kind of coming together, and it ends in a nodal curve which has a boundary node right at this point where the moduli space ends. So here you see some kind of, if you're approaching this like normal Gromov-Witten theory, you would have a problem here, because you count curves of Euler characteristic chi0 for t to the left of this dot in the middle, you get count 1, but when you move to the right, you all of a sudden get count 0. So that's kind of dramatically bad if you want an invariant count. But now the observation is that if you look at the normalization of this nodal curve, you can view it as the middle of a curve family of Euler characteristic 1 bigger. And that family you can show is actually generically a crossing moment. So to the left you have embeddings. With an overcrossing, you come to this nodal moment, and then you cross through. So you see that if you impose this Skein relation, the first Skein relation, that then let's see if this, yeah. Anyway, if you look at the curves in the maybe I'll recall the first Skein relation. So you see overcrossing minus undercrossing is equal to z times splicing. So you see that in the left-hand side you have this maybe hopefully the right one under overcrossing and the splicing, and on the other side you have the other one. So if you equate these things and also say that you count your curves by z to the minus Euler characteristic, you see that if you impose this Skein relation, then the curve count stays invariant. So we're canceling the wall crossing in Euler characteristic chi0 by imposing somehow this relation in Euler characteristic chi0 plus 1. Okay. So this is the hyperbolic case. The elliptic node is entirely similar. And so this one was sort of modeled out x times y is equal to epsilon. This elliptic case is x squared plus y squared is equal to epsilon. And that's different when you do real, in complex geometry, no difference, but in real geometry, there's a difference. And here's what it looks like. So you have a curve in this m chi0. You have a curve with a boundary component that shrinks, and it shrinks. And at some point, the length of the boundary is 0. And then you have an elliptic boundary node. And that one also has a normalization. You see just a kind of smooth curve where this elliptic boundary point looks like a point. And that curve intersects the Lagrangian, right? So now we have these 2 dimensions in 5. And it's a non-generic moment. It intersects Lagrangian. And if you look at the 1-parameter family, it crosses through, okay? So we see that curing this disappearing of a moduli space, unknot disappearing, we see that what's changing in the other family is the linking with the Lagrangian. There is always some kind of problem of measuring this linking globally, but that's what happens. So it's somehow like the other one, but now the curve, 2-dimensional curve, goes through the 3-dimensional Lagrangian. And so it indicates, I'll write this soon, but it indicates that we should count the curves by z to the minus Euler characteristic, and then this a variable actually measures the linking between the curve and the Lagrangian. So then you see that when you impose this condition, that somehow jump on one side, the 2 terms on one side is maybe the first, and then the z times unknot is equal to the other one. So this you come from sort of, I mean, it's like in any crossing, positive crossing to negative crossing. Okay, and the last one, this last framing change, it has to do with how we try to measure this linking. So of course, measuring this linking is a little bit tricky, because we would like to, we have curves that have boundary on our Lagrangian, but we would like to say that, okay, they somehow link with this Lagrangian. So if there were closed curves, then we could just, take its curve, and then we take some chain going off from this Lagrangian, count the intersections. That would be the link. But now they have boundary on the Lagrangian, so we somehow need to regularize. We need to push off the boundary of this Lagrangian, and for that purpose, we fix some vector field along L. It's a 3-manifold. You could take a non-zero vector field, and we assume that somehow generically the boundary of the holomorphic curve would be nowhere tangent to this vector field, and we use it to encode the framing. And then also, since it's nowhere tangent, if we take a 4-dimensional chain which starts out like J times this vector field, actually it's a double chain, so it starts at J and also minus J times this vector field necessary. So then you can try to measure the linking by somehow either pushing off and see that you're free, or just say that, okay, my curve is transverse to this vector field on the boundary, or whatever. It's not transverse, but you know what it's not parallel to the vector field. Count interior intersections, then you get an A power. And now we, of course, have to check what happens when we become tangent. And that happens in 1-parameter families. And somehow this leftmost picture is sort of showing the curve hitting this chain. And as usual, you see that there will be an intersection point appearing there. And if I draw it from the point of view of the boundary with this psi field pointing out to the board, you see this little kink disappearing. And when it disappears, there is an intersection with the 4 chain of the same sign as this crossing. So that's the third Skein relation. So what it all means is then that if we count the curves in the following way, that we take this moduli space of now all perturbed and the rigid curves, we take the number of, if we have such a curve, then it has some kind of orbifold number. That's that number. We take Z to the minus Euler characteristic, A to this linking as measured by this 4 chain we assume it exists, and then finally we multiply it by the class represented by its boundary in the Skein. Then, first of all, we get some element in the Skein, maybe infinite sum, but we get an element in the Skein. And now by our analysis of what happens in 1-parameter family, this count is indeed deformation invariant. Okay, so we have some kind of Gromov-Witten invariant valued in the Skein. So a few remarks about this. So what kind of curves are we actually counting? So this is a little bit technical story, but what we're doing is first what we should observe that we cannot count connected curves. So indeed, because two things can come together and become connected. So we have to do all disconnected curves. But then there is a kind of more subtle point here, and that we are counting what we call bare curves, and we wrote some papers about the rather elaborate task of developing this kind of curve counting. So bare curves are curves that are J holomorphic, perturbed, but we do not perturb the area 0 component. So normally when you do this kind of, any kind of Gromov-Witten theory, you have some curves and you have 0 area curves. So any holomorphic curve you see, it has a lot of solutions that obtained by attaching all kind of constant curve to it. And when you perturb, this will fall into some kind of 0-dimensional, typically infinite thing. But we want to keep those curves unperturbed. And that requires you to do some extra work. Namely, now you have to deal with the fact that so of course your count would be horribly bad if there was a sequence of curves where some constant bubbled off. And we deal with that by some observation that if this thing happens, then there is a trace in the curves from where it bubbled off, some kind of 0 derivative or something like that. And so we have to set up the perturbation scheme so that whatever bubbles off is very close to something you saw before, and that was kind of embedded, nicely immersed, and so on. So it cannot happen. So we can isolate these things. So that's some work, but one should remember that if you want to compare this to, say, kind of approach more like this Amanda's, it's not going to be curve by curve. So our curves contribute quite a lot to such counts. It's a kind of like first term in this Gupkoma-Waffa formula or something like that. Okay, also the sum looks a little bit horrible, and of course there are infinitely many curves, but it's not that bad because, as always with these curve counts, you can filter by area. So below any given area, you have a finite number of curves. So it's not, well, it's infinite, but it's not really. Okay. Okay, so let's do a couple of examples and actually also come to something important. So for later. So what I first want to say. So I first, so the first example I want to do is kind of a very basic thing. So we take a knot in the three sphere, and then we take its co-normal. So that's all the co-vectors kind of killing tangent vector. It's an S1 times R2 in T star S3. Okay, so these two. So we have zero section S3, and we have this co-normal. They intersect along the knot itself. And then I want to make a kind of small non-exact deformation of the co-normal just in a local coordinate around the tubular neighborhood of knot. I shift it by d theta. So when I do that, it's easy to check that there is exactly one holomorphic curve stretching between this co-normal and the zero section, and that's an annulus, okay? And if we restrict to curves going once around this co-normal, so we're in this homology class. In fact, it's also not hard to check that this is the only curve it is, and there is its transversely cut out. So we can now do our Skein count in this class. And the Skein count is first, it's 1 because of, okay, so it's transversely nowhere before this 1. And then it's z to the minus Euler characteristic of the curve, or characteristic curve 0. And finally, we have to take the value of the boundary in the Skein of the two Lagrangians, right? So it would be the tensor product, but I'm suppressing, so it would be the circle in the co-normal times the value of this unknot in the Skein of S3. I'm suppressing the circling co-normal. Shouldn't have, but unfortunately I'm suppressing this. Okay, so this one, if I look at the coefficient for this single circle, then it is A over Z minus A inverse over C. And okay, if you were just given these two numbers, it really does not look much like a cylinder, but it rather looks like two disks, right? Two disks linking the Lagrangian in two different ways. And what I want to kind of try to explain is that from point of view of any sort of Floer homology or anything like that, you have to identify these two in some way. And what's the reason for that? Well, I want to, so maybe I should stay on this picture. So up there, there is a green, something I draw as a Rabe chord. So if we look at this Lagrangian, it is a solid torus, but at infinity, it's a torus times R. And out there at infinity, we can look at curves, which you see down here. There are 4 such curves, actually. But if you allow them to have an asymptotic, a puncture asymptotic to this Rabe chord, then there can be somehow non-trivial curve out there, and we will use them. So they can also be fairly easily computed, actually, by some kind of connection to flow trees, and so by some kind of Morse theory, you can really get your hands at these curves. It's not difficult. For unknot, you can do it in many other ways, but anyway, there are 4 such curves, and I'm sort of drawing them schematically on the Legendrian. So they really live in this lambda u times r, but I project them to lambda u. So there are 2 green dots, which are the endpoints of this Rabe chord. And then they kind of go, so they go from the positive Rabe chord endpoint to the negative one. And you see the 4 curves. So they kind of, yeah, the curves drawn there. And so I can draw them, I can name them by homotopy classes in the torus if I close them up. So I have one, so I can close up maybe by the left little meridian curve there. Then this becomes an unknot. It's P00. They have P10, P01, and P11. And these A powers one has to compute. So A is the A in S3, and AL is the A of of LU. Okay, but that's not so important. But let's now try to understand what's going on with this moduli space. So if I now restrict to maybe forget about this last term, which has an A in it, I look at the lightest curves, what might be going on? So if I look at this P10 curve, that's at infinity, and it's in the left-hand side of this equation, and it's somehow surrounding. If I take my curve count inside seriously, there should be a disk there which has some kind of homology class A inverse, and so this is drawn in green. So when this circle shrinks, at some point it hits this green circle. And of course it can go straight through. So that leaves us, the disk is inside, the curve that's going to infinity now becomes this P00, right? So I took the meridian, I crossed it through the central curve, and then I'm off at infinity again. But of course it doesn't happen, it's not the only thing that happens. When such a thing happens, it also is the case that this moving curve picks up the stationary curve. It's a crossing, so you glue them and you continue. So you see that on this right-hand side, you get the next term, this AL P01, A inverse. So that the A inverse comes from the A inverse in the green disk that we had in the Homfly polynomial. And this AL is because it looks twisted in the solid torus, as in the picture. There's a little kink there. So you see that from point of view of infinity, it's really the case that this Homfly polynomial behaves as if it was a disk. It's like gluing a disk. So what happens in reality, I'm going to tell you soon, but if you have this cylinder, curve comes down, it picks up the cylinder, and then when it starts moving up, the boundary of that cylinder, which is on S3, shrinks, becomes 0, and goes away. Right? And then you're free to go to infinity. But that's somehow the same as if there was no S3 there and there was just a disk. So this it's not like convention. It's something that's really necessary to do. You have to do something of this nature if you want to couple it to some kind of Floer theory. Okay, so let me just explain in different way how this happens. So here on the left you see the unknot cylinder that we had on the previous slide, and now I'm doing something called SFT stretching. So I'm cutting maybe in the middle of this cylinder, and I'm deforming the complex structure, making it very long there. And when I have an unknot, it's kind of not so hard to do this explicitly, and you can check that the boundary circle shrinks until it goes away, right? And when it goes away, there already has to be some other disks there to cancel this thing. So there is some kind of magic moment somewhere before it goes away, where you see a -1 disk born, right? So it's a non-transversely cut out disk that then bifurcates into 2 disks. I mean, this happens all the time in this business. So you see these two, and I kind of mark them A times some disk and -A times some disk. And then in this module phase, you have two kind of one-dimensional manifolds, and one of them just happily moves on. That's the A times the disk, and the other one crosses the Lagrangian at the moment when the circle shrinks. So this kind of magic moment is a consequence of this invariance of Skein counting, of course, but that's somehow how it happens, and you have to deal with this, whatever kind of curve counting you're doing, you have to deal with this moment somehow. Okay. So I want to stay for a little bit longer in this Skein counting introduction, and it's a kind of, I think the not full Skein calculation, in this case, kind of well known, but this is the toric brane, and we can count the holomorphic curves ending on it. So here you see a picture, which is the toric picture, where you have a Lagrangian solid torus inside C3, and there is a formula there for those who never saw it. And from the formula, or from the toric picture, depending on which you like, it's very clear that for this Lagrangian, there is that so if you look in the first coordinate there is this single disk, the red one kind of, that sits on this Lagrangian. And that is the only holomorphic object ending on this Lagrangian, also not so hard to check. But of course, when in our count, we should not expect only this single disk, but it's all its multiple covers with branch points and whatnot, right? So now the kind of goal is to try to understand what does that contribute in the scale, okay? And of course, if you try to kind of approach this directly, it's pretty hopeless, but we can use this curves at infinity trick again. So again, this geometry is very simple, and we can draw this Legendrian torus at infinity, and we can find explicitly by elementary complex analysis or some other means 3 disks that are at infinity, and their boundaries are drawn in this picture. So we have these 3 disks at infinity, and then I'm denoting all the curves inside. Of course, sitting very close to this multi-cover of the disk, I'm calling it Z. Okay? So now we can look at the moduli space of curves which is allowed to have this rave chord up there, and it's a one-dimensional space. So when we take the boundary of that space, it needs to be 0, right? It's some kind of oriented one manifold. And what does it mean? Well, if you think about it, you take one, so take this curve 1. It is in the R invariant region. We push it down. It's going traveling down, traveling down, traveling down. And at some point, it starts interacting with the boundary of the disk, multi-covers of the disk, right? So it's scanning and, picking up some curve and whatnot. But all those moments are in our world not boundaries, because we quotient out by all those relations, right? So somehow it's as if nothing happened. So the only case where you can end is when some piece of the curve again travels to infinity. And when it travels to infinity, we know what's at infinity. It's one of the 1, 2, or 3 curves, right? So the thing that this means is that this sum, maybe one has to be careful with signs here, but this sum is equal to 0 in the Skein, right? So and that allows us to actually determine what Z is. So we have these 3 curves. Again, I denote them. They're curves in a torus, P00, P10, and P, yeah, probably wrong. Should be 01, the last one. I'm sorry about that. 1001. And these 3 curves lives in the Skein of the torus times R. So it's T2 times R. Now that Skein acts on the solid torus by just, it's stupid action, just by inclusion, right? So you have some element in the Skein inside. You take some on the outside, you put it outside. So you can sort of multiply. So it becomes operator on this Skein. And what we're saying is that the first this equation is equal 0. And so it means that this Z is killed by this operator. And as it turns out, these Skeins have been studied in knot theory by Morton and Samuelson and many others. And in particular, there is a very nice basis for what's called the positive Skein of the solid torus. So those are all the curves that are in, let's say, positive homology class. And it's an eigenbasis of this operator P10, the meridian. And there is one, it's kind of distinct eigenvalues, and there is a basis enumerated by partitions of integers. So lambda is any partition. And when you now solve this, it's not so hard because of this eigen thing. When you solve it, you get the following solution. So that I call the partition function of the disk. And here when you invert this operator, it's more convenient. Instead of writing crazy things in Z, you introduce this new variable Q, which is related to Z like the formula. And then you can write a very nice formula, which is like that. So Z here, C is the content polynomial, something. If you have a Young diagram, you take whatever the co-arm minus the co-leg or something, and the H there is the hook length, so that's the hook length in this diagram, and so this is the Skein valued. One should say this is the Skein valued dilogarithm. Becomes dilogarithm if you restrict to symmetric representations. Okay, so we know what one disk or this one kind of you can now also see that wherever some disk sits, it will always contribute like this, except for some, yes.
Some boxes.
Yes, so I think of this lambda as partitions, so Young diagram, and so I have to sum over all partitions.
Yeah, but what's the box in the partition?
So the product is over all boxes in the partition. So for each box I have a content, then I take the product from them.
H is the hook length and C is
content. It's okay. Okay, so that was sort of this introduction to Skein counting, and now I'm going to try to apply it in the Skein trace business. And so the kind of underlying idea where all these things come from that I want to study is the idea that if you have some kind of stack of branes with UN symmetry, you can lift them apart a little bit, and then you should separate them. There should be U1 times U1 times U1 symmetry. And in particular, if you now have this Lagrangian as a special Lagrangian, so deformations of special Lagrangians are given by harmonic one forms, and you can imagine that maybe the local picture should be harmonic one form, but you can look at multi-graphs of harmonic one forms. And so when you have this in dimension 3, then such a multi-graph gives you either just a boring cover, could be, but it can also give you a branch cover where the so you take this Lagrangian, project it to zero section, and it's a cover outside of a link, and along this link it's a branch cover. So it looks like z to the some power in the normal bundle of the link. Yeah, you see what I'm saying. Okay, and so this was studied combinatorially by Knightsky and Jan, and also Geotto Moore Knightsky started this business. And so we are going to now approach this theme using this Skein counting, and the very elementary idea is something like if you have this situation, you have L sitting somewhere, and M sitting somewhere, and L is sitting very close to it. If you want to study holomorphic curves ending on L, you can squeeze L until it lies on M. So then the holomorphic curve would converge to holomorphic curves on M. But it's not the whole truth that they converge only to those curves, but there will also be some thin pieces that are remnants of curves stretching between L and M. But putting these two, if we know the curves on M and we know the curves between L and M, then we should be able to reconstruct all the curves on M. Right? So that's the general philosophy, and I'll tell you how it goes. So here is kind of more carefully the setup. So we have a three manifold, maybe non-compact, have some very long ends we put on it, and we have a Lagrangian inside this cotangent bundle. This Lagrangian may also have some boundary at infinity and so on, but let me not detail it. It will be clear when we come to examples. And inside this zero section Lagrangian M, we have a link. And now I want to take my model. So somehow, as I said, we were interested in looking at any holomorphic curve, but in principle, any link is the boundary of some holomorphic curve, namely the boundary of this little cylinder that comes down from its conormal. So I'm going to use that. So I take any link, I take the conormal of that link. It's a link in M, and then I take the conormal and I shift it outside of L. So L should be thought of as very, very close to M. I shift this one a little bit outside. And now I'm going to count the curves that stretch from NK to L. Okay. So we're going to define this Skein trace. So we start with a link in M, and we now take the curve count that occurs that goes from its conormal down to L. Okay, so not to M but to L. And then this kind of strange formula is just saying that I'm not going to count all the curves. I'm only going to count those which goes once around I'm going to call those that go once around this solid torus central curve. That's what this is the first element in this basis, and I'm taking the coefficient of that. Okay. So that gives me some element in the Skein of L, and the sort of main theorem in this business that we proved with Longy, Park, and Schende is that this map, in fact, this rule, I don't know what it is, induces a map from the Skein of M to the Skein of L. Okay. Yes. By the same little one form. So conormal has a tubular neighborhood in M, and it looks like S1 times D2. And I take this d theta form, just a closed form along S1, and I shift the conormal. It's just happening inside the solid torus. I shift it by that form. And so this L is very, very close. So if I take some epsilon a little bit bigger, it's off. Okay, so I'm saying that this rule actually gives you a map from the Skein of M to the Skein of L, where you have to fiddle a little bit with the A's. So the A variable of M should be the A variable of L to the power N. If the degree of this covering is N, I should have said it. Maybe said somewhere or not, but that's the degree of the cover. Okay, and I'm going to tell you two proofs of this theorem. So the first one is a very direct proof, which actually leads to kind of computations. And then first, what do we actually have to prove? Well, let me go back to this picture. So here we have this nk, and we know that if we move around this nk, this count is not going to change, right? But we would like to show in this theorem that, in fact, this map respects the Skein relation in M. And what we now have to do is we have to check that if I take three links that are related by Skein relations, and I have three different conormals, and I have to check that the counts of these ones behaves as the Skein relation. Okay? And so in order to do that, you can again use this kind of flow graph or flow graph, in this case, limit. And the idea is that you take this middle guy, which is has an immersed conormal, and it actually has some clean intersection there in this Lagrangian. So that Lagrangian is not smooth, but has a self-intersection along a line. So it's not transverse, but clean intersection. And then it's still pretty good for holomorphic curves. And so you can now look at holomorphic curves on that one, which have corners at this intersection. And it's not hard to show that those, by just flow geometry, that those curves with corners are the same as the smoothen curve on the smoothen Lagrange. So this is the first thing, sure. And then, so now I should say we still, now there's no L, it's just in M first, in M. And then we look at this L plus and minus, and we look at the curves that form on them. And when we degenerate them to this immersed person, then there are two possible fates. Either the curves converge to something with corners and some little flow line, or they go through. But those which go through, which somehow they don't care about this intersection, they are on both L plus and L minus. And for those that they go to this intersection, you can show that these immersed curves glue in exactly one way. It depends on some kind of where these corners are located in the R direction. So depending on the ordering, there will be a line or no line. So they go in one way. And so you see that in this equation, in Skein equation, the curves that go through, they cancel in the left-hand side. And the difference between the two are exactly the right-hand side. So there is this little, the Z comes from this little strip attached. Okay, so this is the proof of actually original proof of the Skein relation before I realized all this wall crossing business. But this is the Skein relation in L. Now, in M. Now, if you go to L, one can show that holomorphic curves converge to this big holomorphic curve that we know, and then some thin flow graphs between L and M. And maybe it's a very complicated story to reconstruct this from the flow graphs and make sure they're transverse and so on. But you can show that none of those flow graphs generically go through the point. And therefore, whatever that problem is, it is the same for all the overcrossing, undercrossing. So it's somehow this formula with some standard piece attached to it in all three terms. And so the Skein relation follows. So this was the first and most serious Skein relations. But now let me tell you about the second and third Skein relations to see, and it's also kind of interesting illustration of the fact that this counting is not, this A variable is not kind of completely trivial. So now here, I take two branes. I should do N, but I'm doing two. It's the same thing. So I'm taking two local picture. I have an unknot and I have to lift it. So in M, I have the unknot. I have two local copies of my R3, which are just shifted in the X3 direction. Okay. So now I should do the Skein lift. So I should take all the curves lifted. And of course, there are two of them. One is lifted to brane 1 and one is lifted to brane 2. There's no flow line I can attach, nothing. So just this one. But now when we calculate this number, you see this A minus A inverse, A1 minus A1 inverse over Z. That's the value of the unknot in this first piece of the Lagrangian. And we have to multiply it by its linking with the forechain of the second Lagrangian. And that gives you a power A2. And then this second curve, same thing. I take the unknot in brane 2, and I have to multiply it by A to the power linking with the forechain of the first Lagrangian. And when you think about it, it's actually, this linking is different signs. So it's, the linking can be computed by some rotation of tangent vector, and depending on if you're 1 or 2. But you see that if you calculate this thing, you see that all of it becomes the value of the unknot if the A variable of M is A1 times A2. And that's exactly what it should be. So then we could take it away, and then the polynomial just lifts to the polynomial, right? So it has to be like this. But you see that it's kind of a non-trivial check in some sense, that we have to keep this A variable in mind. The third Skein relation also, so this is also a good illustration, because here actually something happens with the flow lines. And so we take this curve with a kink in it, and we lift it. And again, we lift it to this should be a 2 on the second curve, two separate sheets like this, right? But now you see there is a flow line, namely the crossing. There is a flow line which you can somehow attach to this curve, and the new curve looks like the lower picture there. It has a little boundary on number 2 and the line on number 1. And again, you have to do this calculation with the Humphrey polynomial and take the right A powers, and you see that it's exactly the same thing as first canceling the kink and then lifting. But again, you see that this is actually some kind of dynamics going on here, so it's not completely innocent. Maybe I'll yeah. So I want to mention at least this very, very briefly. So one can show that the Skein of M is equal to some kind of Rabe orbit, so SFT, so generated by Rabe orbits in unit cotangent bundle of M. And so you could in principle define that that's a kind of non-trivial theorem, that they are isomorphic. But if you know that, then you could define the Skein trace by going from orbits down to L. So then it's a normal count. But it's not very, so it's therefore clear there is such a map. But for calculations, this other perspective is much, much better. Okay, so I want to get to do some calculations. So let me say something about these 3D spectral networks, which allows me to, yes. Yes. but okay, it takes a little while. So maybe I'll say it after the talk with some questions. So let me do this first. I'll tell you. Okay. So So I want to give a kind of examples now of double covers of three manifolds, branch double covers, and it turns out there is a nice way of getting a lot of such examples by what's maybe called three-dimensional spectral networks. So we take a three manifold and we equip it with some ideal triangulation. So it's a triangulation where, of course, the vertices here they're at infinity. So that's why it's ideal. Okay, and now we can branch cover each such tetrahedron by the following trick. So on the boundary, this tetrahedron is a sphere, and we take these four dots, right? So we now take a double branch cover, branched at these four dots. So that gives you a torus, okay? And now the first approximation, we just take this torus times r, and we go all the way into the middle of the tetrahedron. And what actually happens right at the vertex is that the Legendrian there that you're going to, this double covered torus, it's actually a copy of this Legendrian that we saw in the toric brane. So if you put it right in the middle. So sometimes you can now resolve this thing as is shown there by smoothing the red dots, and then you would have instead a solid torus inside this tetrahedron. Okay, so that's the toric brane that we saw, and there are indeed three smoothings depending on where which leg you go. Yes.
What is the double?
So the double cover is a cone. So it's a cone. It has a.
I see.
It's a cone on this torus. Yeah, just.
But what happens with the two boundaries when it still gets two boundaries?
Yeah. So it has one boundary at infinity, which is T2, and the other one looks exactly the same, but it's shrinking. So it's like it's like some kind of cone. Okay. So we're going to study holomorphic curves, and we need to understand this sort of background of holomorphic curves for this double cover. And for that purpose, we want to perturb the Lagrangian a little bit. And if you perturb it a little bit, then by some theorems I proved many years ago, you can see the holomorphic curves as Morse flow trees, something like that. And so here is the perturbation of the branch point. So there would be a one parameter family of such things. This is z squared basically, and this is z squared plus epsilon c bar. So that's the generic front of this double point. And when you look at flow trees, there are some special rigid flow trees that goes off there. Let me not explain so much. They have an end and a switch for those who ever read about flow trees. And in the picture, they look like that. So nevertheless, what this will lead to, if you look in this simplex, is a foliation of the whole simplex by boundaries of holomorphic curves with two positive punctures. And this picture should tell you how this foliation, what it looks like. So if I go from the top there, so at the vertices, when I glue everything up, I have some tori, and it's a kind of Morse bot situation with rape chords there. But let's not bother with that. But anyway, so we have a strip going down, and at this down, you can attach either one of the three disks that we found for the toric brane. So that allows you to move off of three of these four red guys. And along the red guys, if you go from one side to another side, you see these two holomorphic disks intersecting, and you can smooth them, and you get these smoother curves. Okay, so that's the kind of picture, and it allows you to give a combinatorial model for the Skein lift when you have a branch double cover. It's the one that was found by Knightsky and Jan, but here in the full scale. But for us, the most important thing that we're going to keep track of are the disks that appear. So the disks appear, so you say from, if you think about this thing, this one, so from each red dot, there are sort of three flow lines going off. So there are three such end sweeps, right? It's C3 symmetric. So there's three flow lines going off. And in this picture, you see that you should imagine some kind of rotating three lines along one of these red ones and along the other one. At some point, they come together, and I find a flow line that connects the red to the red. That is a holomorphic disk. So that's exactly this holomorphic disk that we saw in the first picture for the toric brane. But those are our disks. Okay, that's how they appear in the flow line world. And now let me tell you about some kind of called wall crossing results here. So we can now do the following. So we will take surfaces and we'll transplant them to we will put them in dimension 3. So in this business, you take a surface. That's what people have done a lot before in here. I cannot go through all this why, but it's not so hard. So we take a surface, and inside this surface we take a Lagrangian, also surface, and we assume that surface does not support any holomorphic curve. So it's somehow there's nothing going, there's no holomorphic curve forming on that one. So that's a typical situation if, for example, the surface is actually a complex Lagrangian. So if it comes from, it's a graph of some kind of a holomorphic form, and then you scale rotate it, and now it's Lagrangian, it would generically not have any curves. So then observe first that this Skein lifting map is now algebra homomorphic. So algebra is silly. Algebra, when you have surface times R, is just stacking nodes in the R direction. Of course, if you lift, nothing happens, and you lift again. So this is triviality. But these can still be very useful if we now consider deformations of. So we have the sigma, and we start deforming it in the cotangent bundle, still keeping it Lagrangian. Then you can create a kind of almost Lagrangian. So it's really totally real, but you can control that it's kind of conjugated to Lagrangian areas. So you can make sense out of holomorphic curves on this Lagrangian. And now we can apply the Skein trace map to the corresponding sigma times R Lagrangian. And the theorem says that now there is now an element in the Skein of that sigma times R associated with this deformation, so that if you take any Skein lift of something in the before this isotopy and after this isotopy, then it's related by conjugation by this guy. And the proof is a triviality. So because namely we just take this k first to the left of everything that happens. So then the lift is this k, it just lifts, and then there's kind of curves inside. Lift, that's the k minus times omega. But of course, this thing is invariant under deformation. So I move it over to the right. Of course, the same omega, but now the k appears on the other side. So this is some kind of, if you really do it in deformation, it's kind of non-trivial information. So I'm going to explain. I'm going to tell you something about this in the case when I actually take the Skein. I take k to be empty, which is kind of stupid, but this is just because this is a famous formula. So now imagine I take my surface, my Riemann surface, to be complex plane, and I take the branch cover surface to be the square root of this quadratic differential. So it's kind of famous quadratic differential. And this one depends on two parameters, u, which we view just as deformation parameter of the whole family, and t, which is the family parameter. So it's about running t is my isotopy that I was talking about before. So now I can use the invariance of this Skein lift of the empty knot, which is just then counting the curves forming on this Lagrangian, right? So, and I will count them for u is equal to 0, and for some other u. And for u is equal to 0, I can draw this So this is the kind of slice, the two-dimensional flows, and then as I deform by t, I can check that I first hit one disk, and then after a while I hit another disk, and then so you can draw. It's not so hard to draw this. So this is what happens at u is equal 0. So we see that our Skein lift of the empty link is a product of two disks, right? So the product of two of these functions, z disk, or I'm going to call them psi in a second, on the one hand. On the other hand, if I deform u outside of the unit circle, so for example the 2i, which is a nice value, then we can do the same exercise with the family, and we see three disks instead. So we see first one disk here, and there's a joint flow line, and then another disk. And of course now these things have to be equal. So if I draw them, so these are a thing again, kind of double cover of the plane, so that I can draw them in the torus. And see that so somehow you can draw them anywhere, but the boundaries look like crossing. When I cross through, each one survives, but I have some kind of joint disk, which I call 1, 2. And the thing that we can now conclude is that if I take a holomorphic disk partition function in the Skein, I insert it along 1 and 2, then I get some element in the Skein. I have to multiply all these things, some mess. But that's equal to inserting Skein elements along these three curves. And this sigma is a little twist, so it somehow changes, like change of spin structure. So depending on how many times you go, it's some kind of -1. So this is the, if you restrict to symmetric partition, then this is this pentagon relation for dilogarithm. But this is a lift of that thing to the Skein of solid torus or genus 2 thing, or solid genus. So and there is a lot of kind of identities like this that you can prove in various ways that comes out from this Skein count. So I think I'll stop at that and take questions.